Today we're going to talk about limiting reactants and what that is and how you can calculate them and what you can do with them. The basic idea, as we've talked about in class, is that when you have a chemical reaction, you have two reactants. So like I'm going to just refer directly to your homework because I feel like that is a good idea and it's, make life easier on you. So in this example, you have two reactants. So you have two things that are going to react together to create a product. You have specific amounts of both things. You have a certain amount of each thing. Now, they don't react at the exact same quantity. That like in that 2 moles of nitrogen monoxide, NO, react with 1 mole of oxygen gas. Now, how do I know there's 1 mole? Well, there's nothing here, so you can put a 1 there as a coefficient. Remember that. And then you also have this 2, so it's a ratio of 2 to 1. Now, limiting reactants, when we're basically trying to do this, we're trying to figure out quickly and efficiently which thing is going to run out first in the reaction. That's what we'll call the limiting reactant. That's the thing that stops the reaction because you can't move the reaction forward unless you have enough material, enough reactants of both to keep the process going. Like if you're making a cake and you run out of eggs, well, then you're done. Doesn't matter how much flour. You might have all the flour in the world, but if you don't have enough eggs and enough water and enough sugar and enough oil and baking soda and I don't know, whatever else goes into a cake, it doesn't matter. If you run out of one of the ingredients, then it's done. Same thing goes here. If we run out of one of these, it's done. Now, in this case, we always are going to be comparing moles to moles. So to figure out limiting reactant, if you're given mole values like this, it's actually pretty simple. So you can look at this and you can say, now, which one of these numbers is bigger initially? So clearly, 0.866 moles of nitrogen monoxide is bigger than 0.503 moles of O2. So you would probably guess, well, that's limiting reactant. But again, we have to account for the ratio. That is how much of each thing is used up. So in this case, you use 2 moles of nitrogen monoxide for every 1 mole of oxygen. So what you're going to do is this. In this case, we're just going to divide by the coefficients. So we're going to take our mole value, 0.866 moles of NO, and we're just going to divide by 2. And that's going to tell us that it's going to be what? 0.433 for nitrogen monoxide. We'll do the same thing for oxygen. So that'll be 0.503. Now in this case, we're going to divide by 1 because it's a ratio of 1. So that's equal to 0.503 for O2. So after doing this now, you can see which one is actually smaller. So in this case, which one is smaller? Nitrogen monoxide, NO. That means that will run out first in the reaction, and that makes this the limiting reactant, implying that it's what limits or stops the reaction. Now, something to note, so the next problem helps with this. It says, calculate the number of moles of NO2 that can be produced. So when you have a problem like this where you're given 2 values, you can only ever solve that problem using the limiting reactant. So you must always, so you will start with the limiting reactant or reagent as it's called in this worksheet. I call it reactant. So you'll do that. Now, to do this, you're just going to do a basic calculation now where the point is that you don't care about the 0.503 moles of oxygen. Now, we've established that that is not limiting. It is excess. So whatever is not the limiting reactant is an excess. And if you remember, when you have something that's excess, you cross it off, like for our problem's sake, for solving stuff. So in this case, we're just going to set it up 0.866 moles of NO. Moles of NO, and then we're trying to get to now moles of NO2. So now we're going to get our coefficients. We got 2 moles of NO, 2 moles of NO2. It's 2 to 2 ratio, it's 1 to 1. They're going to cancel out. You're going to be left with 0.866 moles NO2. So that's a really simple version of how limiting reactants are used. Now though, let's do one other one that's a little bit more involved. So the next thing to see, you've got this next problem here. It's quite a bit longer. It's got all kinds of words. The reaction itself is effectively like whatever, doesn't really matter. Because but like you got all this, you got all these words, and when people see this, they're like, oh wow, and it's like no, none of those words matter. This is what you like. Keeping this really simple this year. This is what you care about, the reaction. Nothing really beyond that. So it says which compound will be the limiting. So here's what it says. So it says um, if 7.4 grams, so we've got 7.4 grams of this, and we've got 0.67 grams of nitrogen monoxide, and it's saying which thing's limiting. Now this time they're in grams. So what I suggest you do in a case like this. Now you can never convert. You can never compare grams to grams because so again, it's like clearly, this is a much smaller quantity. Like 0.67 is much smaller than 7.4 grams of O3. We get that. However, you have to account for the molar mass when you do this and the coefficient ratio. So it's not just a simple comparison. You have to do several conversions before you can really deal with this. Now, here's what we're going to do. You see how part 2 here says how many grams of NO2 will be produced? Well, here's what we'll do. To keep this simple, we're just going to solve this part of the problem with both of our values. So we're going to do two problems. And whichever one is smaller, whichever quantity of NO2 is smaller, basing on our calculations here, that's limiting reactant. All right. So, and what I mean by that is we'll start out. So I'm just going to we're kind of doing A and B together. So let's start out with saying we got 7.4 grams of O3. So this is going to be a mass to mass problem, basically. We're going to do a mass to mass conversion here. So we're going to do grams of O3, moles of O3. We're going to grams of NO2, remember. So we'll put moles of O3 down here, moles of NO2 up here, and moles of NO2 on the bottom, and then finally grams of NO2 on top. Now, as far as numbers go, this is 1 mole of O3. I don't have the periodic table anymore, but this number here, this is going to be the molar mass of O3 off the periodic table. So it's going to be oxygen, which is 16. We're going to do that times 3. So 16 times 2 is 32, plus 16 more, 48 grams. So that's from the periodic table. This values coefficients from the equation. Now in this case, the coefficient is the equation is it's actually really simple. There's no coefficients. They're all 1. So it's 4 oxygens, it's balanced. So it's just 1 to 1. There's no coefficients. And then last but not least, we got 1 mole. Now this one over here, it's going to be N plus 2 O's. I'll even write this out to show you. So it's like N is 1. That's 14.01 off the periodic table. Oxygen there's 2 of them. That's 16. That's going to equal 32 plus 14.01. So you get 46.01. So you're going to do all that. I don't have my calculator, so I have to use my phone because the calculator is in my other classroom. So you're going to end up with this one being 7.09 grams NO2. So you're going to do 7.4 times 46.01 divided by 48. And you get 7.09 grams of NO2. And that's starting with oxygen, with ozone, O3. Now, what we're going to do, that was using this. Now we're going to do the same thing with this other problem, because that's the other reactant, and then we're going to figure out which one's smaller. So we'll do the whole problem is going to be the same, except the beginning part, because we're not going to have this be with ozone, it's going to be with NO. So 0.6. So grams of NO. You'll notice that I like to write the units out first. I think that makes it even easier to solve these. And it's like some of you might be complaining, like, oh, I got to do the same problem again. And it's like, yeah, kind of, but I mean, the second part's already done. It's just, it's not that big of a deal. So we're going to have 1 mole here. This value, NO, that's going to go, that's going to be off the periodic table again. So it's going to be 16 for oxygen plus 14.01 for nitrogen. Again, from the periodic table. So that's going to be 30.01, because again, 16 plus 14.01. Coefficients, again, they're just 1 to 1. Simple. There's nothing in this equation. It's all 1 to 1. And then this is exactly the same as this last step. So we already know it's 46.01. So now you're going to do the math again. So it's going to be 0.67 times 46.01 divided by 30.01. So we'll do that. I'm going to check it one more time. I don't like my phone calculator at all. So you get 1.02, or we'll say we'll round up to 1.03. So our 2 possible values, our 2 possible answers are 7.09 grams or 1.03 grams. Now this is a smaller value. That makes this the limiting reactant. So this would be using excess, which that's incorrect. That's not correct at all. It's not possible, because you're using the excess, and that wouldn't be right. That's like again basing how far you can drive your car based on how much oxygen is available in the air instead of the amount of gas in the gas tank. It doesn't work that way. Same thing goes with this. You're basing it on the amount of the initial value, like the correct limiting reactant. So in this case, the smaller value, it actually was limiting here. It worked out that way, but it's just, it happened. So what is the limiting reactant? No, nitrogen monoxide is limiting reactant, actually. So we established that that's limiting. How many grams of NO2 will be produced? 1.03 grams of NO2. And last but not least, last thing we'll do here. Calculate the number of moles of the excess reagent remaining at the end of the reaction. So let's just do this then. At the number of moles of the excess reagent remaining at the end of the reaction. So here's what you'll do. This is actually a very specific question. It's a little, So what you'll do is this. You're going to take the limiting reactant, and you're going to do a conversion from the limiting reactant to moles of the excess reactant. All right? And that's how much is going to be used up. And then what we'll do, we'll take our answer and we will subtract it from our initial value of 7.4 that we're going to have to convert that to moles also. This is all about paying specific attention to units and mainly the units of everything here. This is the kind of question that, this is excessive. I would not give you something this tricky. I might ask you what the excess is, but I wouldn't, like on the test we're going to have, I won't be asking you like, oh, calculate the moles of the excess. It'll just be a straightforward question. So to do this, we're going to go limiting reactant to moles of excess. So that means we're going to do 0.67 grams of NO. We're going to do grams of NO, moles of NO. 1 mole we already, and this is easy because you already know all the masses, like you can just take them from the other parts of the problems. Moles of NO, and then we're just going to go to moles of O3. So we're converting to moles of the excess. In this case, again, all the coefficients are 1. It's a nice problem like that because we just one less thing to do. So 0.67 divided by 30.01, that gives us 0.0, we'll say 22 moles of O3. So that's how much is used up. Clearly not that much. All right, clearly not a lot at all. Just ignore the beeping. And, so we got that. And then now, so that's how much, again, in moles is going to be used up. And it says it specifically wants the number of moles that'll be remaining. So if we start with 7.4 grams of O3, Let's convert that to moles. That's 148. So you're going to do 7.4 divided by 48. So 0.15. We'll round it up to 6, keep it simple. So we'll say 0.16 moles of O3. This is our initial value. This is our initial starting point. We're going to subtract 0.022 from it. All right. That's how much is used up. And then we're going to find out how much is left over. So we'll do 0.16 minus. So we end up with 0.138 moles of O3 left over. That's about as complex a problem as you're going to see. That is probably the most complex problem you've seen in this class at this point in time. Don't freak out, don't flip out. It's not going to be that hard again. But that's just an example of showing you everything that you might have to deal with limiting reactants. It's a basic introduction. We'll walk through more as we move on through the class.